So today I'm going to talk about, well, kind of this. I'm going to talk about encryption and why some things we believe about encryption aren't necessarily true. I'm Colt. I live up in Bozeman, Montana, and do remote Scala full-time. That's just to give hope to people who can't necessarily move to the Bay and want to do awesome things. So I've come to like FP and found that that's like a great way to reason about programs. Total functions like help me eliminate all these weird edge cases. And so recently I joined a startup, Iron Core Labs, and we're doing some really cool stuff with some of what I'm going to show you today. But I started reasoning about it using functional programming, which is not something encryption people normally do. Usually it's all about fiddling bits and getting the most speed, but not about safety necessarily, which is kind of one of the problems. So OpenSSL, like everybody probably knows, HTTPS, everything is over SSL nowadays, and it powers most of the internet. And this doesn't include like IMAP and other things that actually use SSL, or things that use SSL on the command line, like for SSH or whatever. So everybody uses it, and it's probably older than some people in this room. So it must be good. Like everybody's using it, must be good. It's old. Well, no, just run. So but what kind of metric am I using to say it's not good? Well, the test coverage after 18 years or 20 years is under 50%. Like none of us would go to production with software now, like that we wrote in the last 6 weeks, with unit test coverage that low. So it must be rock solid, right? Like clearly it's not tested, but it probably works. No. Nope. So like over the last, this is the last basically 10 years, excluding this year, like these are the number of high, low, and moderate vulnerabilities that have been found in OpenSSL. And it turns out OpenSSL, the more people poke at it, it turns out the more bugs they're finding. And, well, that's strange because like you'd think that they would be like focusing on code coverage now, right? Because people are poking holes in their stuff. But they're just not that concerned about it. They try to test it, and they test it some, but it's hard to test because it's mutable ball of mud, and it's really, really hard to figure out what's going on. So it must be because it's hard. Like it has to be hard, otherwise somebody else would have solved this problem. No. Nope. It's not really, really hard. It's just subtle. And the distinction there is actually like one that I'm going to try to show you today, but it's important. All right, so we're going to cover like elliptic curves and talk about that, and I'll try not to like get too many eyes glazed over when we talk about elliptic curves. It's not scary. It's just some algebra. We'll talk about the laws and stuff, and then we'll actually look at implementation. So, elliptic curves. This is an elliptic curve. It's basically just a curve that is symmetric around the x-axis, and there are points. Like you could solve this equation for any given x or y value, and like that would give you a single point. And anytime you draw a line between 2 points, you end up at exactly one other point. Okay, and that's only not true for values that have inverted x and y, or in the inverted y. And for that point, we call that the point at infinity, and that's treated as like basically our zero case, especially if we're like talking about monoids. So point addition is just find that intersection point and flip it over the x-axis. And this is the entire construction of elliptic curves. Now, I wish I would have put it on one slide so I could have been like Runar and been like, this slide is all you need to know about category theory. But like, I'm not quite that cool apparently. So it's all right. So there are certain laws that hold for this. So the point that goes through P and Q is the same as the point that goes through Q and P. That's pretty obvious. The point that goes through negative Q and Q always ends up at infinity. Like it doesn't ever intersect the curve again. There's an associative law, which is like a little more involved to show, but it does hold. And the identity is like if you add the point at infinity to a particular point, we just assume that comes back to the same point. It gives it the identity. So let's just look at something we want to do in elliptic cryptography is add a point to itself a lot. It's called point multiplication. And so when we add a point to itself, obviously there's only one point. So drawing a line through one point, well, what do you do there? So we use the line tangent to the curve at that point. So that means the line tangent to y equals 0 goes off to infinity, but everywhere else it's defined. Okay? So that p intersects over there when you add it to itself. And just like addition, you flip it over the x-axis, and that's adding p twice, so 2p. What if you wanted to add it again? Well, you just draw the line again through 2p and p, and you just keep doing this. Keep doing it over and over, and you do it hundreds of billions of times or more. Okay? So, like, what are we seeing here? Like, you showed me some curves, you showed me some numbers, and there's a p. Like, well, so in this example, 3 is our private key, which, by the way, would be a terrible private key. Maybe don't choose one that's like, at the bottom of the scale. P is the public generator point. So that's like when people talk about Bitcoin or whatever, there's a public point that everybody agrees upon that is like where everybody starts. So 3 is the private key, and P is the public generator point, and so 3P is our public key. So that's like the number that I send out to the world and say, hey, this is me. That's what we do for GPG or any of those things. You like send out that information to public place. But like, all right, still I haven't told you anything. Yes, Stu?
3p being p plus p plus p, or 3
yes.
plus p? Okay.
Yes, 3p is 3 times p, so p plus p plus p. Yep. Okay, so let's just take a quick example. So if n is Bob's private key, and m is Alice's private key, got to have Bob and Alice in any crypto presentation, then np and mp are the two public keys. So what this is really used for, though, is elliptic curve Diffie Hellman, which is really just a fancy way to say if you have somebody else's public key, you can use your private key to come up with a shared secret. So, and then you can use AES or Salsa 20, or you can use any symmetric key encryption you want at that point. But you've got to come up with a shared secret. So, like, why does that work? You might be like, well, this seems like dark magic. Well, we talked about commutativity and associativity and whether or not you can add points over and over again. Well, NP and multiplied by M is the same as moving the N's and M's doesn't matter. Okay? So this is just math. Like, we've talked about some math, and these are well-known algorithms. Like, they're equations, and everything is good. Well, I kind of lied. So what we saw when we saw that pretty curve is when we evaluate this thing over the real numbers. Well, real numbers go on for, well, forever. So like, we don't want to represent those as bits, because how would you represent something that was 1,000 bits long? Like, well, you want to constrain it down to a certain size. So the first thing you should think of is, well, what if we just modded all these numbers by p? Like, we just invent some prime, and we mod everything by that prime. Well, if you evaluate a curve, mod a prime, this is what it looks like. It's not a curve visually anymore, but it still is a curve and holds all the laws that we just talked about. And because of that, you can basically take and add any 2 points on this scatter plot together, and you will get another point on the scatter plot. And where that point is cannot be determined except for by doing the work. There's no way to like reverse engineer it. And that's really important, because if you could reverse engineer it and figure out, then you wouldn't have to really solve much of a problem, would you? Like, you just reverse it and everything would be really, really bad on the internet. So this is called point multiplication, and this is the algorithm to do it, like to do it over and over and over again. This algorithm is not really that important other than it's Haskell, and I just wanted to put it on the slide. But really, the math is looks almost identical to the Haskell, and I thought this conveyed it slightly better. So it's just doubling the point and then dividing the n by 2 each time. So what do we say when we mean large? I keep talking about these numbers, and we use 3 in our example, which is bad. So this is the number of atoms in the universe, ish. And this is a prime that is chosen for I think this one is specifically the Bitcoin prime. But anyways, it's 2 orders of magnitude off, but this number is very, very big. And these are 256-bit primes. Now we're getting into more 512-bit primes. So number is twice as big as the number of atoms in the universe. So we're talking really, really big numbers. So it turns out, when you have these huge numbers and you have a curve that is not pathologically circular or some dumb curve, that this problem right here on this slide is hard. Very, very hard, thousands of computer years hard. And so that's what the entire security of the internet is relying on, because OpenSSL, under the hood, just does this elliptic curve Diffie Hellman, and if you have that shared secret, everything is compromised. So this basic math that we've just talked about is the entire basis for the way that the security works inside of OpenSSL. Now, I'm going to show code, and it would be irresponsible of me to be this thing is so easy, you should just go and start using this code in production, that kind of stuff. Crypto is very subtle. There's side channel attacks, there's constant space and constant time algorithms, there's different point representations to avoid doing inversions. There's all kinds of very subtle things, but that doesn't mean that the underlying core stuff that we're going to see here today is wrong. It's just I'm not going to bet my career on it. So I said finite field, or I said we're going to operate with that scatter plot. Well, all that really means in Scala code is this. Don't let somebody create this FP type with an I that's arbitrary, first mod it by some prime. You might be wondering why I don't use mod here instead of writing my own mod. Well, it turns out mod in Java or on the JVM gives you the remainder, not the actual mod, and that's a whole deal too. But just don't put a % in there. It's not going to work. So I wrote this field. If anybody's worked with Spire before, this is just a field implementation using the Spire type class. And so this is just showing that full implementation. And it's very trivial. I mean, we're just negating values and modding them by primes and multiplying them and adding them. It's not hard. It's just math. OK, so what about points? I said they had an x and a y, and we had to solve that equation. Well, I guess if we're going to be good functional programmers, right, we're going to use some parameter. We're parameterized on type A until we absolutely can't. So let's make it parametric and see what happens. So it turns out that there's other representations of points. There's x, y, and z so that you can carry along this remainder. And there's stuff that's really clever math tricks that allow you to do cool stuff, which I only mention so that if you look this stuff afterwards and you're this paper doesn't talk about affine points, it talks about homogeneous points or Jacobian points or something else. There are weird tricks that people use to get better performance in certain situations, but they are all isomorphic to each other, so they can go back and forth very easily. So let's just look at affine points. So this is the implementation for adding 2 affine points. So note here that the affine point is over some arbitrary type A, and I enforced that that A has a field implementation. Well, we just showed field for FP. There are field implementations for many things, including complex numbers and other really crazy things. But this implementation is completely abstracted away from from the underlying field definition. So now we know this should work for any field. That's what we're asserting, at least. I haven't shown any proof of that. So I won't go through this code extensively. It's a well-known algorithm for finding the slope of the line and yada, yada, yada. So I used doubling points in that point multiplication. That's also really easy. You find the line tangent to the curve at that point. Again, just a math problem, not hard. So that's actually pretty easy too. Also, continue to note, like we're talking about some parameter type A on the affine point. So this is that nice Haskell definition turned into some Scala that has a tail rec, and I want tail calls so bad. So yeah, this is that same thing, but I implemented it in Scala just to show like it could be done. So it turns out that if you have all of those things I just showed, that points themselves form a group, an additive group. So all we need is the ability to add a point over and over and over again to do elliptic curve cryptography. And so if all we need to do is add things over, all we need is an additive group. As we need to add and we need to negate, that's all we need. So this is the definition for that. And if you run this through Scala check for thousands upon thousands of times with different field definitions, you will always get the right answer. Like, it will tell you that it's lawful every time. Okay, so you might be thinking, like, so what? Well, what I just showed was like, this point implementation and all of the code that I showed today doesn't rely on the underlying like bit patterns. It doesn't rely on anything to do with that. All it's doing is like, it's just doing very general math, and we know by the laws of parametricity that like nothing fiddly is going on here. So if we find a bug in our system, we don't need to like, oh, did we screw up point multiplication? No, we know for a fact we didn't screw up point multiplication because we proved it with the laws, right? So we're in the place where we can know things about the way that points work without thinking about the way that the numbers work, without thinking about the way that the complex expressions work that we're using for these x's and y's. We can prove things about each individual piece, which is what we want to do as functional programmers. Like, I want to prove this piece works, and move on. Now, yeah, if you've done any crypto before, you know the reason that people fiddle all the bits is because it's slow if you don't fiddle all the bits, and it is. Like, there's no doubt. Like, this isn't a panacea where like I've invented this cool thing that's like faster than OpenSSL and everybody's happy. Like, this is slow. Especially this code that I show is very slow. Like, it's using big int. It's not using proper new types, so it's like boxing sometimes, and it's terrible. So you can solve those problems irrespective of this particular solution, though, because you can get a different numeric type underneath this, and as long as that numeric type works, you're still good, and you can test that independently. So I just don't understand why people are so scared of crypto, and like anybody I talked to at this conference leading up to this, they were like, well, crypto's scary. And I'm like, yeah, like it's not great in terms of like, I mean, it's very subtle. Like, side channel attacks are super scary. Like, what if I use different amount of voltage on the CPU during this time? Like, that stuff is scary, but like, people just believing that crypto is good because it's old is not right. And we need to like individually test small pieces and move on. So like I'm building stuff on top of construction similar to this, using pairing-based cryptography and some other stuff that's not in most crypto libraries. And when we get done with it, like, I'm going to have to send it off to a bunch of people to like try to get it reviewed and get researchers to look at it. And like, there's going to be a bunch of work. But as a community, especially as a functional programming community, like, we should be getting behind things that are testable and things that are good and things that we can reason about, instead of just being like, oh, well, it's old, so it must be good. So like, I thought by the time we got to 2017, like, we'd have like flying cars and hoverboards and maybe like crypto that was tested. But like, since we didn't get those things, like, I guess I'll just have to settle for us moving in the right direction for crypto. So thanks. So I don't know if I